You are looking at the largest group jump ever. It's also known as the and took place in Singapore in 2013. At the time, it broke the record for most people jumping rope simultaneously. Over 47,000 people participated. The previous record was held by South Africa and was nearly half the size of the Singapore jump. But what if everyone on Earth suddenly decided to jump? How high would we go? To answer this question, we need to know how high someone could jump if no one else was around, which is known as a vertical jump or squat jump. But before we get into that, do you think humanity would be able to jump up higher than a building or higher than a mountain? Let me know your thoughts below. The average vertical jump for an untrained teenage boy is between 16 to 24 inches. A professional basketball player can reach almost double that height. Some can even jump higher than that. For example, Shawn Kemp once jumped 12 feet in the air during an NBA game. That's almost as high as a giraffe is tall. Spiking volleyball players like Yana Karpazova can reach even greater heights when running full speed. She once spiked a ball while jumping over 14 feet in the air. And although this isn't directly related to jumping, a person can actually jump higher if they start falling first. During a test conducted by Harvard University, trained individuals were able to jump 30% higher after free falling for 10 seconds. So if everyone on Earth jumped and fell for 10 seconds before jumping, we would collectively go a lot higher. But for now, let's assume everyone just jumps without any preparation. So the next question is, how much mass does it take to affect the outcome of a jump? If you asked me this question a few years ago, I would have said it doesn't matter how many people are jumping, as long as everyone is doing it at the same time. But since then, I've learned that there is something called conservation of momentum. This means that the total momentum of a system remains constant in the absence of any actual forces. To explain this, imagine that no one is on Earth and you decide to jump. You jump up and down a few times and eventually come to a stop. Now imagine a friend joins you and decides to jump too. Your friend's jumping cancels out your downward momentum, so you end up floating in space until you both fall back down to Earth. Now imagine a third person who starts jumping while you and your friend are still falling. Their upward momentum cancels out your downward momentum, so you start floating again. This keeps going on and on. Theoretically, if enough people were jumping, they could keep us off the ground forever. So if a person can jump 18 inches and we want to know how high we could jump if everyone jumped at the same time, we'll need to do some math. Force equals mass times acceleration. To find the force we need to lift everyone off the ground, we can use 9.8 meters per second squared, which is the standard acceleration due to gravity near the surface of Earth. We know the average mass of an adult is around 62 kilograms, but we also need to account for children under the age of 10. Children on average weigh about half of what adults weigh. So the average person weighs around 31 kilograms. At the time of recording this video, the world population is around 8 billion. So the total mass of everyone on Earth is roughly 248 billion kilograms or 248 million metric tons. Multiply that mass by the acceleration due to gravity, and we find that we need a force of 2.43 trillion newtons to lift everyone off the ground. Now multiply that force by the distance that we want to move the mass, which is the height of the jump we're trying to achieve. In this case, we're looking for a jump height of 0.45 meters or 18 inches, which is the average vertical jump for a 16-year-old boy. Multiplying those two values together, we find that we need approximately 1.1 trillion joules of energy to lift everyone 18 inches off the ground. But wait, we're forgetting something. The human body has a natural tendency to resist changes in motion, which is known as inertia. The more massive an object, the more inertia it has. As a result, the force required to overcome the inertia of a group of people will be greater the more people there are. For example, if I push one person with 100 newtons of force, they'll accelerate at 10 meters per second squared. But if I try to push 10 people at the same rate, they'll only accelerate at 1 meter per second squared. Because of this, the total force needed to jump will increase by a factor of 8 billion, which is the number of people on Earth. So the total force we lines need to lift everyone 18 inches off the ground is 19.8 trillion newtons. And if you remember earlier, we calculated that we only need to point for 3 trillion newtons. So this means we won't be able to jump, at least not without some outside help. But what if we had that help? What if we lit every single candle on every single birthday cake on Earth at the exact same time? Every year, there are around 135 million birthday parties celebrated around the world. Each party has at least one candle, and each candle burns with an average power of 10 watts. Multiply those two numbers together, and we find that on an average day, there are around 1.35 billion watts worth of candles burning. In 2021, the global capacity to generate electricity was around 63.8 terawatts. So the power output from all the candles on Earth is about 0.02% of our total electrical capacity. But what if we somehow turned all of that electrical power into potential energy? Potential energy equals mass times gravity times height. If we assume that the entire electrical output of the planet is stored as potential energy and used to lift people off the ground, we can solve for the height. Using the same values from earlier, we find that the maximum height we could reach is about 0.3 meters or 9.2 inches. Still not very high, but what if we could use the energy released from nuclear fusion reactions? Nuclear fusion is the process that powers our sun and other stars. When two hydrogen atoms combine to form helium, they release an incredible amount of energy. In fact, our sun releases around 400 billion watts of energy through nuclear fusion. So what if we built a giant fusion reactor big enough to power all the birthday candles on Earth? Using the same calculation from earlier, we find that the height we could reach with the energy produced by our giant fusion reactor about 153 meters or 500 feet. That's still nowhere close to any buildings on Earth, but it is more than high enough to clear Mount Everest. So if we could harness the power of nuclear fusion, we could jump high enough to touch the sky. But what if we didn't need to burn candles or perform nuclear fusion? What if we could jump higher just by existing? This may sound crazy, but scientists believe it's possible. There's something called quantum entanglement, which occurs when two particles become linked together in such a way that they share the same fate no matter how far apart they are. Entanglement has been observed between photons, electrons, atoms, and even larger molecules. But because of the uncertainty principle proposed by Werner Heisenberg, entanglement cannot exist between objects of significant mass. The uncertainty principle states that the more precisely the position of an object is known, the less precisely its momentum can be known, and vice versa. This means that even if we were to perfectly entangle all the particles on Earth, the resulting jump would be minuscule. So unfortunately, we'll never be able to jump high enough to touch the sky. But there's still hope that we can jump high enough to see the stars. A few years ago, a group of researchers in Austria came up with a solution that might allow us to jump higher than a building or a mountain. They proposed building a structure that would spin rapidly in one direction and contain a series of platforms inside of it. People would stand on the outer edge of the spinning platform, and as the platform began to slow down, they would jump off and onto a lower platform. This process would be repeated until the bottom platform reached the ground and everyone could jump off and continue on their way. It may seem complicated, but the concept is really quite simple. The trick is to build a structure that can spin fast enough to allow everyone to jump off and land safely. And if you think that sounds impossible, just consider this. NASA once spun a wheel faster than the speed of light. Okay, so maybe making a structure that spins fast enough to allow everyone to jump off isn't so crazy after all. If you like this video, make sure to check out my latest video on how long we can survive on Earth. Thanks for watching.